Of today. Our first speaker for this session is Philipp Hauke from University of Trento, telling us about quantum simulation of holographic quantum matter.
Yeah, thanks a lot for the introduction, and it's really a pleasure to be here in this great conference. Thanks a lot to the organizers for making this possible. Yeah, before I start with the actual topic, I was asked a couple of times, where's actually Trento? So I just want to give you very quickly an idea. So Trento is in northern Italy. It's, if you want, midway between Milan and to the north there's Innsbruck and Munich. So Trento is traditionally in one of the few north-south connections between Southern Europe and Central Europe. And has been always a place where ideas and merchandise and so on have been transported. So Trento is a beautiful city in the Alps. It's not quite the same size as New York, it's very beautiful. But the important thing is we have a very high density of institutes working on quantum science and technology. So we have the center QTN, which was founded in 2018, which actually is the first such quantum center in Italy. And so we have University of Trento, Bruno Kessel Foundation, INFN, CNR, Pitevsky, BC Center, ECT Star. And so this gives a very high density of researchers active in the field, and which allows us to work on all aspects of quantum science and technology, from foundations to experiments. We're also active on technology transfer and education. So if you get a chance to pass by Trento, then please visit us. Okay, good. Enough publicity. Let's come to the topic. Okay, I want to talk about holographic quantum matter. I'm going to introduce this in a few minutes in a bit more detail, but just to give you a very brief heads up why people think this is interesting. It comes actually out of cosmology, quantum gravity, string theory, where this type of field theories that I'm going to talk about, this matter, is dual to a bulk gravity theory. Okay, so there's a connection to black holes there that we're going to see. It is also very important for quantum information, as these are the fastest scramblers of quantum information that we can imagine in nature, and they are phenomenological models for strange matter. Strange metals. And as I'm going to try to show you, they're also very interesting for quantum technologies and quantum simulation. Okay, so we're going to see all of these aspects. So here's the outline of my talk. I first want to introduce you a little bit what is this holographic matter actually, how we should think about this. And then I want to come to the actual results, which is a proposal for implementing this in the cavity QED. Which also, I think, is nice because we have seen various platforms here, but we did not yet have any talk, I think, about cavity QED, so cold atoms in a cavity. So I think it's also nice to see something of that. And then depending on how I'm doing with time, I also want to talk about briefly about non-stabilizerness in one of these iconic models, the Sachs-Defier-Kitaev model. Yeah. Okay, so let's start. What is this holographic matter actually? So this comes originally from string theory. So okay, I'm not a string theorist, so I give you, let's say, a pedestrian point of view on this. So essentially, by the way, so this is what I'm going to recount. This is very nicely written in much more detail in this review by Hardnall, Lucas, and Sachdev. Yeah. Okay, so in string theory, the objects of interest are these brains that you may know, which are high-dimensional objects. There is a certain string theory of three-dimensional brains, where at weak string interaction, okay, you have these brains, and then there are string states connecting them. Yeah? Now, the string interaction tells us how strongly these brains gravitate. So if you go to strong string interaction, they become very heavy, so to say, and they collapse. And they build what one calls a black brain. So essentially, think of a black hole. Yeah? So now one can wonder, in this theory, in this string theory from weak to strong string interaction, what is the effective theory that describes this, or what are the lower-lying excitations? On the one side, these are these strings that connect the brains, which carry the dynamics. In the strong coupling regimes, it's the metric. So we're talking about the general relativity. So it's the metric close to the horizon, which has the low-lying excitations. And now one can wonder, okay, what is the theory that describes these, the effective emergence theory at low energies? On one side, this is supersymmetric Young-Mills, so it's a non-abelian gauge theory at weak coupling. And on the other side, this is actually a classical gravity theory, ADS5, again in weak coupling on the gravity side. And well, so if you increase the coupling of the string theory, you go from supersymmetric Young-Mills to ADACE-5 gravity, right? On the other hand, if you increase coupling in Young-Mills, you go from weakly coupled Young-Mills, well, to strongly coupled Young-Mills, right? And so the insight of Maldacena was that these two things, so well, you increase coupling, and with increasing coupling, you go to ADS5 gravity or to strongly coupled Young-Mills. Well, these are actually the same theory. Yeah, so this was the insight by Maldacena. And this is what one calls the ADS-CFT correspondence. So we have an ADS gravity theory on the one side, and it corresponds to a strongly coupled field theory, in this case, Young-Mills. Yeah. We can wonder, equal in which sense? Well, one way to say two theories are equal is when the partition function, given a certain set of parameters, equals. And so what does it mean on the field theory side, so on this Young-Mills side? Well, one can add to the path integral, one adds source terms, which are given by, the strength of these is given by parameters hi, coupled to certain operators, which can be particle densities, currents, or whatever. Okay, so this gives some parameters to adjust in the theory on this side. On the other side, what are these parameters? Well, turns out that these are the boundary conditions of the gravity. Okay, so you have the bulk gravity, and then you fix the fields on the boundary. And this defines actually the entire gravity fields through the entire bulk. It's not trivial to show that this is a Dirichlet type of boundary problem. It's not trivial to show that it's actually a well-defined boundary problem, but it works out. Huh? Okay, and so in this sense, then people say, okay, so this means that essentially we can think about this thing that we have a gravity theory which is defined by a field theory at the boundary. So this field theory, if you know what is going on in the field theory, you know what's going on in the entire bulk of this gravity theory. And this is why it's called holographic matter, because in a hologram, you look at a three-dimensional object, but actually everything about this three-dimensional object is encoded in a two-dimensional photographic plate, right, in a lower dimensional thing. And so here it's exactly the same thing. You have in spirit, let's say, you have a higher dimensional gravity theory, and all information about this gravity theory is encoded in a lower dimensional field theory. Why does this actually work? Well, this works because we are not here in our usual three-dimensional space, for example, but this is actually hyperbolic spaces. Okay, so the surface area scales of such a hyperbolic space because it's this fractal type object. So the surface area scales exactly in the same way as the volume. Usually we think, okay, so if you have a ball, the volume scales as r cubed, the surface is r squared. Here actually both volume and surface scale in the same way, which is very weird to think about it. But this means that the boundary can have exactly the same amount of information as the entire bulk. That's why it works. Okay, so here we see this first, this is why this is called, because of this principle, holographic quantum matter. And this is the first connection that I showed you, the first tile connection to black holes. But there are also now immediate physical consequences. Namely, black holes are the objects that absorb quantum information or information in the fastest way possible. So if you perturb them, they extremely quickly relax back to equilibrium, just given by a scale which is the inverse temperature of the black hole. And on the field theory side, one can translate this and see that perturbations are immediately scrambled among the entire system. Notice this scrambling of quantum information given by a scale which is just 1 over the temperature. So the microscopic scales of the theory disappear. We have only 1 over temperature. Actually, Maldacena, Schenker, Stanford conjectured that there's nothing that so the influence of chaos cannot develop faster, essentially, than this time scale. So the Lyapunov exponent, the inverse of this, the maximum that you can have, so the exponential decay, is given by the inverse of this time scale. Yeah. So that's why we see this. So these are essentially the objects that are most chaotic or that lose or distribute quantum information the fastest way possible. Okay, so you have this connection to quantum chaos and quantum information. So the second tile that I showed you in the first slide. Okay. Now we can wonder which field theories can actually saturate that bound. And so we can wonder, okay, so if we have quasi-particles, what do we have? Well, if they have a gap, then we need to see how likely is it that there are quasi-particles and that they can scatter, so we lose the information. Then we see that it goes with e to the mass divided by temperature, the time scale. Then we say, okay, what about gapless quasi-particles? It goes with 1 over t squared. Yeah? Now if you go to low temperatures, then these are values that are much larger than 1 over t. So these systems can scramble information much slower, if you want. So these field theories must be systems that do not have any quasi-particles, which happens exactly in strange metals. And so there's this connection to condensed matter. The difference is why people from condensed matter also excited about this holographic quantum matter. And so this is the third tile that I showed you. Yeah? Okay, so this is very exciting, interesting, many connections. So yeah, let's do this. Let's do holographic quantum matter in a quantum simulator. Well, unfortunately, these field theories, they're usually very, very complicated. I mentioned supersymmetric Young-Mills. So this is the Lagrangian. Just to give an idea, the 11 fields that describe this, it's a non-abelian gauge theory. We've seen exciting progress on quantum simulating non-abelian gauge theories, but we are not quite at the supersymmetric Young-Mills yet, unfortunately. Yeah, so you have all these one spin gauge boson, spinor fields, scalar fields, and so on. Then we could look around. There's other famous models like the Banks, Fischler, Schenker-Susskind matrix model. But also there you need a model of matrices, and then you want to send the matrix dimension to infinity, and you have 9 of these, and then there's matrix valued spinors of spin 9, and so on. So there's lots of degrees of freedom. Okay, so one can wonder, are there actually not simpler models that we can use? And there was a breakthrough in this in 2015 when Kitaev gave a talk at KITP, which was called a simple model of quantum holography, where he proposed the following model. Okay, it's a model of spinless fermions, which can be complex fermions or Majorana fermions. It doesn't matter. If they're complex, it just means that you have a charged black hole, but doesn't matter much. And it immediately was actually realized by Sachdev and then also others that this was a model that was very closely connected to an SUM disordered Heisenberg model that people had been looking at already like 20 years earlier. Okay, so it's a model of fermions that interact. You have n fermionic modes, but what makes this now complicated is that you need an all-to-all interactions between all these fermionic modes. And not only do we need all-to-all interactions, these interactions need to be completely random. Okay, so each of these ijkl is taken from an independent Gaussian random distribution. Okay, it's a complicated model, but actually, so it's okay. It has a holographic dual. Because the simpler model, it's a simpler dual, so it's Jakiv-Teitelbaum gravity for the experts. But okay, but this model, it fits all the bills. So we have, I just mentioned, we have the holographic dual. We have fast scrambling. This is known. It doesn't have quasi-particles and so on. So we want. So this is like, let's say, I would say maybe the simplest model that we know of right now. That is. Or one of the simplest models that makes sense in this holographic relation. Yeah? Okay, but so now we have this main characteristic of this model is this disordered all-to-all interactions. And this is also the main challenge, I would say, because so it's not enough just to say, well, let's do a model with infinite range interactions, or let's put some disorder there. Some diagonal disorder. So for example, think about a spin model where we have some long-range hopping. This is a model with a power law hopping, tunable with a tunable parameter alpha. When alpha becomes small, this hopping becomes long-ranged. And then if you put a perturbation in it, you might think, okay, the perturbation spreads very fast because you have long-range hopping. But actually, exactly the opposite happens. So if you put a perturbation here, it just stands there for a very, very long time. This comes because there's a destructive interference effect going on. Now you can add, you can say, oh, let's add the disorder. Maybe we mess everything up. Well, if you add the disorder to this thing, you just get Anderson localization. And again, a perturbation that you put just stands there. By the way, this is a theory, but this is actually an experiment done in a trapped ion platform in Innsbruck where Peter Jurcevic was sitting somewhere. I think I've seen him in the audience. He was in Innsbruck back then, now he's with IBM. So, he was one of the main driving force of these experiments. Okay, so it's not just enough to make things long-range interacting or some diagonal disorder. We really want these disordered interactions. The disorder has to be in the interaction of these fermionic models. So it's hard, but people have actually come up with proposals for that. So there are various in analog platforms and also several digital proposals. Well, but these analog platforms, they're very, very hard experiments. And the digital ones, well, until a month or so, previously showed this, this slide. I just wrote there's a challenge with the scalability. People have looked only at less or equal to 7 fermionic modes, so very small systems. There's actually been a very recent paper, this one here, by Granet et al., where they managed to go to 24 fermionic modes by encoding into 12 qubits. To do this, they had to use a sparse version of SYK and do some tricks, but it's very nice. So there's progress here. But I still believe that there's space for thinking also about other platforms. Yeah? Okay, and this brings me to the actual, let's say, results. This after this introduction, but I think it's worthwhile to think a little bit about what we're actually trying to do here. So this is, we want to implement this Sachte-Vier-Kitaev model in a cavity QED setup, okay? So the essential idea is we put atoms into a photonic cavity, there's some disordered speckle pattern, and in the end we get out this disordered SYK model. Okay, and since we have not seen this platform, I'm going to walk you through the steps how we aim to reach there. Yeah? Okay, so let's start with, so we have a cavity, we have 2 mirrors, which actually means that if you think about a photon traveling in this cavity, it has to have nodes on the mirrors, because otherwise you would, if it travels back and forth, you would get a destructive interference. So this is not sustainable. So there's only certain frequencies allowed that give you a standing wave in this in the cavity. You can also look at transversally. So make a cut through the beam, and one sees that there are also higher transversal modes, which also have different numbers of nodes. So depending on the geometry of the cavity, this can be given, for example, by the Hermite-Gauss modes. The fundamental one is just a Gaussian profile, and then you have different numbers of nodes. Okay, so now you choose to tune a system to work with one single cavity mode, since all these are now only discrete frequencies are allowed. You can identify one frequency and say, okay, this is now my cavity photon. So the Hilbert space of this thing is given by the occupation of this single photon mode. How many photons do I have in this mode? And so the corresponding spectrum is, let's put the 0 photons to 0, the ground state, and then at the frequency of omega cavity, you have the first excited photon. And then, of course, it goes on 2, 3, 4, 5. But we'll just stick to the very low excitations. Okay. Now, okay, that's very fine and interesting, but now let's add the atoms into the game. So let's assume that we put like a pancake of atoms that can take 2 states, ground and excited, into this cavity photon beam. Now, the Hilbert space becomes a tensor product between photon number and ground or excited atom. Okay, so we extend the spectrum. Let's put the atom in the ground state orbital and 0 photons to the 0. So at some energy difference of the orbitals, we have the atomic energy. So this is excited state with a 0 photons, and now this 1 photon, what it actually means? Well, it means we are still in the ground state of the atom, but we have 1 photon. So, and then there can be detuning, so one can choose, for example, with the distance of the mirrors, we can tune the frequency of the photons, so we can have different detunings between the excited state and so 0 photons, but the excited state atom, and 1 photon in ground state. And now, because of the dipole interaction between atoms and light, they can actually exchange interactions. Okay? So it's like this photon is driving a sort of a Rabi oscillation between the ground and excited state atom. Okay, so now the Hamiltonian that describes this in second quantization is this one here. So we have, I don't know if I can, maybe we can point. Yes. Okay, so we have, we annihilate an atom in the ground state and create one in the excited state. But to do this, I need to get the energy somewhere, so I annihilate a photon from the cavity. And okay, so here I put in back spatial dependence because it's actually a pancake of fermionettings. It's a cloud. Okay, and so this picture up here is a little bit simplified. This would be if I have a pinned 1 atom standing somewhere. Now, how strong this happens, well, it depends on the dipole interaction between the atom and the light, but there's actually also spatial profile. So depending on how the pancake agrees with the nodes of the mode, the transversal node that I've chosen, for example, this one here. Then in the center, I have zeros of my cavity photon, so there will not be any interaction. But here I have a maximum interaction. Okay. What is nice now, so all these atoms, they sit in the beam of the photon altogether. Okay. So so what can happen is that somewhere an atom, if I find it in the excited state, it emits a photon at some place, and then another atom at a different place catches that photon and goes to the excited state. Yeah? And so this means they can talk all to all, transmitted by the cavity photon. Yeah? It's actually not dissimilar from, if you know trapped ions, no? The phonon bus, you change your spin state, and the phonon transmits the excitation to someplace else. It's the same mathematics here. So this is nice, this talks to all atoms, but as we said before, we want these interactions to be random. Here's too much structure there. It's not random. So this is not, it's very interesting physics that one can do with this type of system, but this is not what we want. Okay, so the first thing that we do is we think that actually instead of using a single mode, we need to mess everything up. So to do this, we need many modes so that we can add up different disorders. One can think of a multi-mode cavity, so it's one that sustains various modes. One can also instead just trotterize through a single cavity mode, which is what we've worked out down here. By the way, I forgot to mention, this is actually, all of this comes out from a very fruitful collaboration with the groups of Jean-Philippe Pontu and Julian Sonner. So Jean-Philippe was really the one who triggered this collaboration like 5 years ago. So he came to me and said, I want to do the quantum simulation of the SYK model in my setup. Don't we want to collaborate on that? So it's a very exciting journey that we're having together. Okay, so now we take a multimode cavity. So now the Hilbert space is the occupation of all the different modes that I label with M. And so if you go back to the spectrum that we had before, then it can be now, the atom can be in the ground state, but we can have an excitation in different modes. And all of these can exchange between the excited state atom and the cavity photons. Okay, so which means I can go from ground state to excited state by absorbing any of these cavity photons, and then I have different detunings depending on which mode I'm looking at. To boost the interactions, what we need is we need also to add an external drive. So there's a coherent laser beam from the side, which has a given frequency and a Rabi frequency and a detuning. So actually this detuning there we measure with respect to the drive frequency. That's not so important. But now what this does, this drives now Rabi oscillations between ground state and excited state with the Rabi frequency given by omega drive, and with a certain detuning delta D. Yeah? Okay, so now I don't want to show you lots of Hamiltonians. We can think about this much more pictorially. Just this upper line here, we can actually write a sort of a Feynman diagram like this. So here what is happening? Well, a ground state atom comes in, it emits a photon, and then it becomes an excited state atom comes in, emits a photon, and becomes a ground state atom. And of course, the inverse process is also possible. So you read the time, so to say, from bottom to top, but you can also have the emission conjugate and absorb a photon. Okay, and the lower line gets, okay, a ground state atom comes in, it interacts with the drive, and then becomes an excited state atom. Okay, so these are our two, let's say, elementary interaction vertices that we have. And now the idea essentially is to hook them up in a way that the only resonant process is when you have a ground state atom, it interacts with the drive, becomes an excited state, emits the photon, becomes ground state again. This photon is captured by another ground state atom, which is now excited, interacting with the drive, it becomes again a ground state atom. Yeah? To do this, well, we have to essentially choose, so this is two levels of perturbation theory. The first one is that we say, okay, let's take this detuning here large, okay, so we essentially eliminate this step here, and then we also take this detuning to be large in the second step, which means that we need to go back. Okay? And then so we hook them up, and then what's happening? We have now the excited state has been adiabatically eliminated. So we have so essentially, if you look at it, you have two ground states that come in, and they scatter in some way, and we have two ground states that go out. Okay? So in an effective interaction vertex, we get 2 fermions come in, scatter, and 2 fermions come out. Okay. And so one can make all of this rigorous by doing perturbation theory and so on, but I think this is a bit too tedious. You can look it up in the papers. So. I'm doing okay. There's one last ingredient that we need. Is a bit slow. Okay, that's fine. The one last ingredient we need to mess the things up. We need to make them disordered. So what we can do is, to do this, we have imagined to insert a speckle pattern, and now we do it in a way that this speckle pattern goes into the interactions. So to do this, we put here to go to an auxiliary level, put this is blue detuned from this auxiliary level. So what it's going to do to introduce an AC Stark shift on the excited state. So now this detuning is no longer the same all over the pancake, but now it depends on where in the speckle pattern the atom sits. Okay, we get the disordered detuning. And now, if we look at this, well, where was this detuning? It's the energy of the excited state above the ground state. So here and here we have actually this detuning. So if you eliminate this with perturbation theory, this propagates into the effective interactions. Okay? And so we get disordered interactions out. Okay, now this all sounds nice, of course, but now the question comes, does it really recover the SYK physics that we want? And to do this, we did numerical simulations, really looking at all the microscopic details. And I think in this context, at least, so people have not done it in this detailed way. So really, we generate a random speckle pattern, put in the mode profiles and so on, tune all the different parameters, and then simulate what interactions come out. And so, well, are they random? Yes, so we are able to randomize these. So this, we have a broad distribution now of interactions. But I said in the beginning we would like to have a Gaussian profile. This is the Gaussian. We are a bit off, and we rather get the Cauchy distribution. And so in many papers we read, okay, we do this or other proposals before us. We do disordered, some disorder there, and then limit of large numbers. This becomes Gaussian, and so we are happy. But so they said, okay, the Gaussian has to come somehow. No? So we tuned all the parameters. It cost us 3 months tuning parameters through all the different regimes, and the Gaussian was just not coming. Then we went, we were a little bit depressed, but we went back to some of the other papers, and we saw in some of them where they have also done these calculations here. These were some kind of actually to provide us with their data. We saw that in their paper they showed, okay, we have a random distribution, and it's sort of close to the Gaussian here. So it depends on the parameter regime and so on. Also, but if you do a fit, actually they also have a Cauchy distribution here, and in this other paper, here they have it's more Cauchy, here it's more Gaussian, so depending on how you tune. Okay, but it seems that this is actually something, people have not considered that before, that this comes out sort of naturally. But it appears to be actually quite common in these types of setups. And because there's additional, some correlations between the interactions that are still there that you cannot get rid of. Because they're not completely random, but they come from these mode profiles and so on, okay? But so I want to show this also because what I find nice about this, that thinking about this experiment, it stimulates also new types of theory questions. Now you can wonder, is this actually an admissible randomness profile? Do we still get the same physics? So we did lots of, I'm not going to show this, but we did lots of calculations to show that actually the Cauchy distribution is fine. So certain quantifiers, the autocs and spectral form factors and so on, they all go to what we expect from the Sachs-Tafir-Kitaev model in large systems. Okay? So this is, I think it's an interesting question, how far can I go, how far can I push, also taking experimental realities into account and still get the right physics. Okay, well, as you may have seen, this is it's going to be a tough experiment, but actually the group of Philipp, they've already done first steps. So they did a simpler thing. They just wanted to test if they can do the speckle pattern and get disorder in this cavity and so on. So they made simpler models, a central mode model, a disordered Lipkin-Meshkov-Glick model, and saw interesting physics. For example, for the first time they observed these gray polariton states. They also saw a finite size localization transition. So even intermediate steps, they're interesting because they just add to this disorder cold atoms toolbox that we're having. Okay, so they're already worthwhile to do that. We don't have to wait until we have the final result to do something interesting. Okay, in the last, I just want to spend a very few minutes to discuss the last results that we are, some newest results that we are having on looking at the complexity in these models, and so not only SYK but also random matrix theories that show a localization transition. So it's about complexity transitions. So one can wonder what distinguishes actually a complex quantum system. Well, if you go to Wikipedia, you look at what is a complex system. It says, okay, the basic definition is you have many components that may interact with each other and in a way that is interesting. So it's rarely completely deterministic, chaotic, and you can get emergent behavior and so on. Okay, so it's a general definition of complex systems. But actually, what makes a quantum system complex in a genuinely quantum way? Well, one thing that one may think about immediately, say, okay, it's quantum, it has to have massively distributed entanglement. And in the context of quantum simulation, it's actually nice that Feynman in this famous talk, Simulating Physics with Computers, he states somewhere, he talks about the Bell inequalities, but essentially says, okay, there's entanglement is there, non-locality, okay, and that's the difficulty. That's why we cannot seem to be able to do this with a classical computer to simulate quantum systems. Okay, so we want to have massive entanglement. But now we know that this is not all. There are massively entangled states, like the ground state of the toric code, but actually can be described easily with classical computers. There's the famous Gottesman-Nil theorem, which says essentially, if I can get my state by applying only unitaries from the Clifford group, so C naughts, Hadamard gates, and S gates, then this outcoming state, psi here, I can actually calculate easily classically. And the reason is that these are many states that I can generate, but they are countably many. There's a discrete number of such states. And then one can show it's actually not enough for a universal quantum computer. What we are missing is the T-gate. So we have to be able to add lots of non-trivial phases to the thing also, not only entanglement. Okay, so if we sprinkle in some T-gates, we have now a state generated by generic unitary, then this now becomes, one can show, exponentially difficult for a classical computer. So what's nice is that actually generating these T-gates is also hard for early fault-tolerant machines using the surface code. So it seems to be there's no free lunch somehow. Huh? But now one can look at, okay, how much does the state that I have deviate from a stabilizer state? So this, well, if you generate it with the Clifford, it's called a stabilizer state. So this is what you can call non-stabilizerness and magic. So if you're able to, in your machine, to generate a non-stabilizer state, then this can do something that you cannot compute on a classical computer, which is exponentially hard to do on a classical computer. So we can say that if I have such non-stabilizer states, they are sort of resource for quantum computing. Okay. So now to come back to what I was saying before, now we can say, well, this SYK, this looks very complex, right? So this should have lots of this stuff, this non-stabilizerness and magic. And so we looked at different markers for things of like complexity. We looked at the inverse participation ratio, the entanglement entropy, and the measure for this non-stabilizerness, which one calls the stabilizer-Renyi entropy. I looked at what this does. Okay, so, as we go from the SYK model away from the SYK model. Okay, so to do this here, and this is a theory analysis. So we add to the SYK model now written with Majorana fermions. We add an Ising model, which with the Jordan-Wigner transformation we can map also to Majorana, so the same language. So we go from something that is very complicated to something that is an integrable model, a very simple one. And so what we find is the following thing. So on this side, we have the SYK model, and then we tune continuously to the Ising model. And we see that indeed there is, on this side, all these markers. So participation ratio, which means we have many states involved, we have lots of entanglement, and we have lots of non-stabilizers. All of these are high. So we have this high complexity region, and then it drops very abruptly. And there seems to be even like level crossings. In other models, we can really do finite size scaling and show the critical points. Here it's a bit more difficult. Why is it more difficult? Because actually, as you increase system size, it seems that this critical point, it moves. So this region here becomes actually smaller, okay? Which means that, okay, at very large systems, we expect that we are not allowed to add an epsilon perturbation of Ising model to the SYK model. But this is actually known that this is very sensitive towards small perturbations with two local terms. Okay? But what is interesting, so this at finite sizes, this is really a broad window, and so one could think about maybe these complexity markers that can show us where is this window where things still reproduce the physics that we actually want. Another interesting feature is that actually you see that the participation ratio and the entanglement entropy, they are much more well-behaved than the non-stabilizerness, which seems to be non-monotonous. These are different system sizes here. What we understand is actually because the SYK model has different symmetries depending on the number of Majorana modes that I have. And so this is interesting that this non-stabilizerness seems to be the only one of these three that is sensitive towards that. Okay, I need to wrap up. So what I wanted to show is that cavity QED can be an ideal platform to pursue this physics. It's also an ideal target for quantum simulation, I believe, because it has this very high difficulty for classical computation. And as I showed you, there's also lots of interesting physics on the road just on thinking about disorder models. And thinking about these stimulate many further questions. So for example, how can we actually in these experiments observe extreme features of chaos? We saw universal quench dynamics in the SYK model that came out from these considerations, which could be like a first observable. The question comes, what do these imperfections actually mean? So for example, if you don't have long-range interactions, we looked at this in one paper recently, or these actually open systems, so what does it mean to have a quantum chaos in presence of dissipation? And with this, I need to thank the team and also thank you.
Maybe time for one quick question, since we're over time.